Look around you for just a second. Power lines outside your street. Chargers on your table. Extension boards under your desk. Cables behind your TV. Wires inside your walls. Even the internet depends on massive networks of cables under oceans. For more than 100 years, electricity has been treated like something that must travel through metal. Copper wires became the highways of modern life. And because of that, our world was designed around plugs, sockets, adapters, transformers, and endless charging cables. But here's the question that sounds like science fiction, yet is actually real science. Can we send electricity through the air the way we send Wi-Fi? And if the answer is yes, then the next question becomes even bigger. Are power cables eventually going to disappear? Wireless electricity is not a new dream. In fact, the idea is older than most people realize. And the most surprising part is this. Wireless electricity is already happening today, just not in the way many people imagine. Before we go further, we need to clear one confusion. When people hear wireless electricity, they imagine something magical, like energy floating freely in the air, filling a room, and powering everything. But real wireless electricity works differently. Wireless power transfer means electric energy is moved from one place to another without a physical wire connecting them. That's it. And there are multiple ways to do this. Some methods work only at a few centimeters, like your phone wireless charger. Other methods can work across a room. And some methods can work over long distances, even kilometers, but they come with serious challenges. So wireless electricity is not one single technology. It's a whole family of methods, each with its own strengths and limitations. To understand the future, we need to understand the basic science first. And that science begins with something invisible, but extremely powerful. Electricity is not only current inside a wire. Electricity is connected to two invisible forces. Electric fields. Magnetic fields. And when these fields change, they can push energy through space. This is the key idea behind wireless power. A simple example is a transformer, the device inside many chargers. In a transformer, electricity in one coil creates a magnetic field, and that magnetic field creates electricity in another coil. No direct metal contact is needed between the two coils. Now imagine separating those coils slightly. If you bring them close, the energy can still jump from one coil to the other through the magnetic field. That is exactly how most wireless chargers work. So when you place your phone on a charging pad, it's not receiving electricity from air. It's receiving energy from a magnetic field created by the charger. This is why wireless charging works best when the phone is very close and properly aligned. The moment you increase distance, the magnetic field weakens rapidly and efficiency drops. So wireless charging is real, but it is not unlimited. And this brings us to the first major method of wireless electricity. The most common wireless power method is called inductive power transfer. It's used in wireless phone chargers, smart watches, electric toothbrushes, wireless earbuds cases, medical implants in some cases. The idea is simple. One coil produces a changing magnetic field, and another coil receives it. It's safe, reliable, and cheap. But it has a big limitation. Distance. Inductive charging works well only when the receiver is extremely close, usually within a few millimeters to a couple of centimeters. That's why your phone must sit directly on the charging pad. If you lift it even slightly, charging stops. So if you're imagining a room where your phone charges while you hold it in your hand, induction alone can't do that. Induction is like whispering, it only works when you're right next to someone. To power devices across a room, we need a stronger and smarter technique. And that takes us to the next level of wireless electricity, a method that feels almost like tuning two musical instruments to the same frequency. Induction is great, but it's short range. To move beyond that, engineers developed something more advanced called resonant wireless power transfer. Resonance is a simple idea. If you've ever pushed a child on a swing, you already understand it. If you push randomly, the swing barely moves. But if you push at the right timing, the right rhythm, the swing goes higher and higher using the same effort. That is resonance. In wireless electricity, resonance means the transmitter coil is tuned to a specific frequency. The receiver coil is tuned to the same frequency. Energy transfers more efficiently, even at a longer distance. With resonance, the coils don't have to be almost touching. They can be separated by a few inches, a foot, sometimes even several feet. This is the method people often imagine when they think of charging through air. Some experimental systems can charge devices on a table without precise alignment. Some can power sensors and small electronics across a room. But even here, there are limits. Resonant power transfer works best when the distance is not too large. The receiver is not blocked by heavy metal. The environment is controlled. The power requirement is not huge. So yes, resonance brings wireless power into a new category, but it still doesn't replace power cables for large energy needs. To understand why, we need to go back in time, to a man who believed wireless electricity could power the entire world. When people talk about wireless electricity, one name always appears. Nikola Tesla. Tesla wasn't just an inventor. He was a visionary who imagined electricity as something that could be distributed globally, without wires. In the late 1800s and early 1900s, Tesla experimented with high-voltage coils that could create massive electrical discharges. His famous device, the Tesla coil, could generate dramatic sparks and electromagnetic fields. Tesla believed that Earth itself could be used like a conductor, like a giant electrical system. He dreamed of a future where homes receive power without wires. Ships and factories draw energy remotely. Electricity becomes like a public broadcast. At the time, this sounded impossible. But Tesla was not guessing randomly. He was working with real physics, resonance, electromagnetic waves, and the conductive properties of the ground and atmosphere. His biggest attempt was a project that became legendary and unfinished. The Wardenclyffe Tower. Tesla built Wardenclyffe Tower in New York around 1901. It was huge, expensive, and ambitious. Many people believe it was meant for wireless electricity. And it was. Tesla claimed the tower could transmit electrical energy without wires over long distances. But it was also designed for wireless communication like radio, before radio became mainstream. Here's what Tesla wanted. He wanted to send power using a combination of high-frequency electrical oscillations, ground conduction, electromagnetic energy in the air. In theory, it could work. But the tower never achieved its goal. It ran out of funding and was eventually abandoned. People often say Tesla failed because the world wasn't ready. That's a nice story, but it's not the full truth. The real reason Tesla's dream collapsed is much more practical, and it still affects wireless power today. The biggest enemy of wireless electricity is not technology. It's physics. When you transmit energy through space, it spreads out. And as it spreads, the energy density drops quickly. This is why a light bulb looks dimmer the farther you go. A speaker sounds quieter from a distance. A Wi-Fi signal becomes weaker in the next room. The same happens with power. If you try to broadcast electricity in all directions, most of the energy is wasted. Only a small fraction reaches the receiver. To send useful power, you must either keep the receiver close, or focus the energy into a tight beam, or use extremely high power levels. Tesla's tower was facing this same problem. Even if he could transmit power, it would be inefficient, hard to control, potentially dangerous, expensive compared to wires. And that's why investors lost interest. Because from a business point of view, a copper wire was still the best solution. Simple, reliable, efficient, cheap. So Tesla's dream didn't die because it was impossible. It died because it wasn't practical at scale. But today, something has changed. Modern electronics, better materials, and smart control systems have revived the idea not to replace every power cable, but to remove many of them. And the next part is where wireless electricity becomes truly exciting, because now we move into long-distance methods that can send power like a signal. So far, we've talked about wireless power methods that work close range, induction and resonance. But if we want to transfer power over long distances, we need a completely different approach. This is where things start sounding futuristic. One long-distance method is microwave power transfer. The concept is straightforward. 1. Electricity is generated normally. 2. That electricity is converted into microwave energy. 3. The microwaves are transmitted through the air. 4. A receiving device called a rectenna captures the microwaves. 5. The rectenna converts them back into usable electricity. Microwaves are already part of daily life. They carry Wi-Fi signals, satellite communication, radar systems, cellular networks. The difference is power level. Normal communication signals are weak. But microwave power transfer uses much stronger energy so that the receiver can collect enough power to run real devices. The key advantage is focus. Microwaves can be directed like a beam. That means the energy doesn't spread everywhere. Instead, it's aimed at a target. This instantly improves efficiency compared to broadcasting electricity in all directions. And yes, this method has already been demonstrated successfully in real experiments. Another method is even more visually dramatic. Laser power transfer. It works like this. Electricity powers a laser emitter. The laser beam travels through the air. A photovoltaic receiver, like a solar panel, converts the light back into electricity. In other words, it's like sending power as a bright, concentrated flashlight. Laser power has a major advantage over microwaves. It can be extremely precise. A laser can hit a receiver on a drone or a device with high accuracy, especially if tracking systems are used. But lasers have major weaknesses too. They are easily affected by fog, dust, rain, smoke, clouds. Even heat distortion in the air can reduce efficiency. And unlike microwaves, lasers bring an obvious danger. A powerful laser can damage eyes instantly. So laser-based wireless power is real and promising, but it requires strict safety control and controlled environments. This is why you don't see laser charging in normal homes. But you do see it in one place where wireless power makes perfect sense: machines that need power without landing. Here's a question that immediately grabs attention. Can a drone stay in the air forever if we beam power to it? The answer is, in some situations, yes. This is not a fantasy. It has been demonstrated. A drone can be equipped with a lightweight receiver, a rectenna for microwaves, or a solar receiver for lasers, a power management system. Then a ground station sends energy upward. The drone uses that energy to keep its motors running. This idea is extremely useful because drones are limited by batteries. Even the best consumer drones typically fly only 20 minutes, 30 minutes, maybe 45 minutes. But if power is delivered continuously, flight time becomes limited mainly by mechanical wear, weather, and system reliability. This could change many industries: surveillance and security, disaster monitoring, border observation, communication relays, environmental research. Some people even imagine permanent drones acting like small satellites in the lower atmosphere. However, there's a big catch. To keep a drone in the air, you need a focused energy beam. And a focused energy beam creates one unavoidable problem: safety. This is where wireless electricity hits its biggest real-world barrier. When you send power through the air at high levels, the air is no longer just empty space. It becomes part of an energy system. If you're using microwaves, too much exposure can heat human tissue. Animals and birds could pass through the beam. The beam must be controlled and regulated. If you're using lasers, the beam can cause instant eye damage. It can be dangerous to aircraft. It can even create fire risk in certain conditions. So wireless power beams cannot be treated like Wi-Fi. Wi-Fi is safe because the energy level is extremely low. Wireless electricity, if you wanted to replace power cables, would require power levels thousands to millions of times stronger. And that means it must be targeted, tracked, shut down instantly if interrupted, restricted to controlled zones. So yes, we can beam power. But we cannot beam it freely across a city without creating a safety and regulation nightmare. This is why most real wireless power applications today focus on short-range charging, industrial environments, sealed systems, medical devices, controlled drone charging experiments. Now the big question becomes: if long-distance wireless power is risky, and short-distance wireless power is limited, then are we really heading toward the end of power cables? Or will wireless electricity remain a niche tool? That answer is in the final part, where we connect all the science to the real future. So after everything we've covered, let's be realistic. Wireless electricity is not going to erase every power line overnight. But it absolutely will replace cables in places where cables are annoying, fragile, expensive, or unsafe. The first areas where wireless power will grow fast are the ones where even a small improvement has huge value. For example, medical devices. Doctors already use wireless power for certain implants, because you can't keep opening the body just to replace batteries. Wireless charging through the skin is safer than surgery. Factories and warehouses. Many industrial machines move constantly. Cables wear out. Connectors break. Wireless power systems can reduce downtime. Smart homes and small electronics. In the near future, it's very possible that you'll have furniture, desks, and tables that charge devices automatically without you thinking about it. Public spaces. Airports, cafes, and cars are perfect places for wireless charging surfaces. People don't want to carry cables for every device. And then there's the biggest area of all. Electric vehicles. Wireless charging for EVs is already being tested. The goal is simple: park your car and it starts charging automatically. No cable. No plug. No forgetting. So wireless electricity is not one giant revolution. It's a slow replacement of cables in the places where wires cause the most friction. Now, let's address the biggest misunderstanding. Many people imagine a future where electricity is just floating around a room, and every device pulls power from the air like magic. That future is unlikely. Not because it's impossible, but because it's inefficient and unnecessary. Think about how much power your home actually uses. A phone charger might need 10 watts, 20 watts, maybe 30 watts. But a home appliance needs far more. A refrigerator, 100 to 300 watts. A microwave, 800 to 1,500 watts. An air conditioner, 1,000 to 4,000 watts. An electric heater, 1,500 to 3,000 watts. If you tried to power these wirelessly across a room, you would need huge energy fields or beams. And that would cause problems. Wasted energy. Interference. Safety issues. Higher cost. Complex regulation. So the truth is, even if wireless electricity becomes common, your house will still rely on wires behind the walls, just like today. Wireless power will mostly replace charging cables, adapters, low-power device wires, temporary connectors. The heavy electrical backbone will stay wired because wires are simply too efficient. Now let's talk about the most exciting and realistic long-term idea: wireless charging roads. This concept is being explored in several countries, and it makes perfect sense. The idea is to embed wireless power coils under the road surface. Then, electric cars with a receiver coil underneath can charge while parked, stopped at traffic lights, or even moving slowly. This could solve one of the biggest problems in electric vehicles: range anxiety. Instead of building bigger and heavier batteries, cars could use smaller batteries and charge more frequently through infrastructure. Even if roads only charge in bus lanes, taxi zones, highways, delivery routes, it could still reduce battery size and cost dramatically. This is where wireless electricity becomes more than convenience. It becomes a strategy for reshaping transportation. But again, it won't replace every cable. It will replace the cables that are most inconvenient for humans. So, is this the end of power cables? Not completely. The future won't look like a world with no wires. It will look like a world where wires are hidden, automated, and less visible. Think of it this way: cables won't disappear, but they will stop controlling your daily life. You won't constantly search for chargers, untangle wires, replace broken cables, fight over sockets, carry adapters everywhere. Instead, wireless power will become like a background service. Phones will charge on tables. Earbuds will charge in your pocket case. Cars will charge while parked. Medical devices will recharge safely. Factories will run with fewer weak connection points. And in special situations, power beams, microwaves, or lasers may even keep drones in the air for hours or days. So the real story is not electricity without wires everywhere. The real story is wireless electricity will remove the most annoying cables first and slowly make the world cleaner, simpler, and more automated. And once that happens, you'll look back at today's world of charging cables the same way we look back at dial-up internet. It worked, but it was clearly not the final stage.
Subscribe Info Beyond Borders now for more mind-blowing knowledge.